So this is section 3.2, talking about graphs. Really the introduction to graphs, I think. So first off, let's say what even is a graph, because that's important to know. A lot of people think even in calculus have a hard time answering that. What is a graph? So what is a graph? A graph is a visual way to represent all of the points that work for the function. And what do I mean when I say work? So if you look at this point here on the graph, if you look at where it is, that looks like it's at 1 and 1. That's at x equals 1 and y equals 1. And notice when you plug in x equals 1 and y equals 1, you get an equation that's true. Because what's 1 squared? What's 1 times 1? 1. And so like that works for the equation, I would say. And then you look at another point, like maybe right here. Where's that point? 1, 2, 3, 4, and 2. And see how that's because when you plug in 2 into the function, you get 4. And it's important to recognize that all these other points here, like right here, that works for the function too. It's just harder to plug in exactly. And it's harder to estimate because it's not like perfect. But every single place on this line works for the function if you would plug it in. And then just while we're here, notice that this function works just the way it does, because even if you take these negative numbers, like right here, when x is -1, if you plug -1 into the function, if you make x equal to -1, well, -1 times -1 is +1. And so that's why it's positive on both sides, because when you plug it in, it will be positive. And notice it's just the same exact thing for all of these graphs. Here, see, it goes down. You have something like right here, where x is -1, y is -1. Just simply because what is -1 cubed? Well, -1 times -1 times -1 is still -1, because two of them cancel out, but you still have one. And so that's why that goes down on the other side. But anyway, that's not even what we're trying to look at with these. We're just trying to talk about what a graph is. Well, that's what we were saying. For here, we're trying to say if they're functions. Because we can have the graphs of not functions. That's fine. They're just not functions. So let's clear off what we wrote so we can look at them better. So what does it mean to be a function? Let's remember, a function means that when we put one thing into the equation, for each thing that we put into the equation, we only get out one answer. And let's remember again that when we talk about what we're putting into the equation, we're talking about the x values. So when we talk about for each x value we put into the equation, are we only getting out one y value? That's the question we're asking here. And when we look at this first graph, and that's why they drew these vertical lines, because there's something called the vertical line test. So the vertical line test just says that if it's going to be a function, every single vertical line that you would draw has to cross through only 1 point, or less than 1. But it cannot cross through 2. And if there's any place on the graph you can put a vertical line where it crosses through 2 points, then it's not a function. So you see this one is a function. It passes the vertical line test. This one, also a function. Because everywhere you draw this line, it only crosses through 1 point. Now you come to this one and you see they showed you 1, 1, 1, -1. So here, this is saying when we put in x equals 1, when we go 1 equals y squared, we get out two different values for x. And you can see that in the equation too, right? Because if you tried to solve for y, you'd have to square root both sides. And when you square root both sides, you always get two answers. So that one is not a function. And you see the same thing with this. They don't label the points. You don't even need to know the points. That's what's the beauty of graphs, is they show you so much about the function without actually calculating it. All of these vertical lines we draw here, except for these two right on the edge, all go through 2 points. And so if there's even just one, if there's any place that goes through 2 points, that means we're putting in a value and getting out two separate values. And that means that it's not a function. So which of these are functions? Just the first two. And that doesn't mean there's anything wrong with the second two. They're just not functions. So you got to do like other stuff with them sometimes. All right, so let's read this question first. Let f be the function whose graph is given in figure 15. So there's the graph we're talking about. The graph of f might represent the distance y that the bob of a pendulum is from its at-rest position at time x. Negative values of y mean the pendulum is to the left at the rest position, left of the at-rest position, and positive values mean it's to the right at-rest position. Right, so that doesn't even totally matter for the function, for the question, because they just give us the graph. But this is what they're talking about. I guess I can even do that. That there's a pendulum that's swinging, and when it's below the x-axis, it's talking about being on one side. When it's above the x-axis, it's talking about being on the other side. And so the distance is like, this is 4 inches away, 4 inches away, 4 inches away on either side, just going back and forth. So, I mean, that is true that if you had a pendulum, the graph would look somewhat like this. It looks like this is assuming no air resistance or gravity, but it's okay to assume that sometimes. But that doesn't even matter for this. We're just trying to answer these questions. So let's look. A, what is f of 0? So again, what does that mean, f of 0? I mean, this is critical. This is one of the most critical things to know. It's not hard to know it. You just have to know it. Is what does this notation mean? This notation means that x is 0. You're putting 0 into the f function. So that's the x coordinate, because x coordinate is always what we're putting in. And so notice, what do we get when we put in 0? We get 4. So that just means that f of 0 is 4. So normally we do that for, well, not normally. A lot of times you do that with an equation, but you can do that with a graph as well. That just means that's the x value. And notice that it can't mean that's the y value, because if it was the y value, you'd have 3 different outputs. You'd have 3 different answers. But what we know about a function, if you're doing a function of something, you should only ever get one answer. So this is what we're saying. For the next one, the x value is 3 pi over 2. So you just go to the graph. Looks like that's right there. When we plug in 3 pi over 2, we get 0. And then when we plug in 3 pi, we get negative 4. That's all we're doing there. All right, so what is the domain of f? Well, the domain is just the possible x values. So you might be tempted to say just like anything, because it looks like if you continue this pattern out, it would continue like this. But if it cuts off, that does matter when you talk about domain. They do want you to talk about that. So what are the x values here that it's going through? It's starting at 0, and it's going to x equals 4 pi. And we'll put brackets on that because these are closed dots here, not open dots. And then what is the range? Well, the range is just the same for the y values. So this one, even if it did repeat, the range would still be, looks like from negative 4 at the very bottom to positive 4 at the top. So another way I like to think about domain and range on a graph is, well, I guess with domain, it's like talking about the vertical line test. It's like if we do a vertical line, if it's part of the domain, then it'll cross the vertical line. So like here, your vertical line doesn't cross any graph. So these numbers are not part of the domain. But then when you get here, it does cross the graph. So all these numbers are part of the domain until here again where it doesn't. And then we'll do the same with the horizontal line for the range. So it's like down here, this horizontal line doesn't cross the graph. But then here, starting at negative 4, it does cross the graph. And it crosses the graph all the way up until 4 when it stops crossing the graph. So don't get this confused with like the vertical line test or the horizontal line test, but you're just showing the range is wherever this vertical line, wherever the graph exists. So wherever this vertical line crosses the graph. And so that's going to be from negative 4 to 4. Again, brackets because these are closed dots. So list the intercepts. Recall that these are points, if any, where the graph crosses or touches the coordinate axis. Right, so there's a bunch of them, right? I don't want to list them out, but we'll start with the y-intercept. So what's the y-intercept? It's right here, 0, 4. And then glance at the x-intercepts. Look how there's a bunch of them. And so think about this. Can a function ever have multiple y-intercepts? What do you think? If there was another point right here? No, right? Why not? Because if there were two y-intercepts, when you draw the vertical line right here, it would cross through 2 points. So that's just a nice little thing to keep in your mind, that a function is always going to have only one y-intercept, but it can have as many x-intercepts as it wants. There's no problem with like it crossing a horizontal line. It's just the vertical line. So that's just something to keep in mind. You always have only one y-intercept. You can have no y-intercepts, actually, but you can't have two if it's a function. And then the x-intercepts, they're just right here, because they're always the points that cross the x-axis. Another good thing to point out here, I don't know if I've pointed this out before or not, but look at the x-intercepts. Look at the y-coordinate of all of the x-intercepts. It's 0. And that just goes to show that always, no matter what, if you have an x-intercept, the y-coordinate's going to be 0. And so that's always how you find x-intercepts. If you have an equation and you got to find the x-intercept, you set the y value equal to 0 every single time. Doesn't matter what the equation is. Even if it doesn't have to be a function. If you set the y value equal to 0, you'll find the x-intercepts. And similarly, to find the y-intercept, you're going to set the x value equal to 0. And again, that can be with a function or any type of equation. Of course, if there's a function, you should only get one. But if there's an equation, you can get multiple, and that's fine. But that, no matter what, every single time, no matter what class you're in, find the x-intercepts by setting y equal to 0. Find the y-intercepts by setting x equal to 0. Okay, for how many times does the line y equals 2 intersect the graph? Well, let's just draw it. Let's switch colors. Brown, a lot nicer than a lot of people think. And let's draw the line y equals 2. So remember the line y equals 2. That's everywhere where the y-coordinate is 2. And we'll just say, how many times does that cross the graph? It crosses the graph here, 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 and here. Crosses the graph 4 times. So f, for what value of x does f of x equal -4? So notice here, they're not saying that x is -4, right? They're saying the function f of x is -4. And so when they say that the whole function is -4, they're talking about the y value. And so here they're saying, where's the y value? -4. And so notice that's actually pretty much exactly what they asked on the last question. We're saying the y value is -4. How many times does that cross the graph? How many times is the graph itself -4? And 2 times. So yeah, another way they could have phrased this question is, how many times does f of x equal 2? And it would have been the same thing. All right, G. So for what values of x is f of x greater than 0? So they want, when is the whole function going to be positive? So f of x, that's the y value. So we're looking for where the y value is positive. So just look at everywhere the y value is positive. It's positive there. Now I guess the weird thing here, and they do say, for what values of x? So whenever we're thinking about something like this, you're thinking about the x values. Pretty much always when you're listing places on the graph, you're thinking about the x values. For what x values does this happen? So like when we list out this interval, kind of see it as a number line now. Like we're going to list from 0 to pi, from 3 pi over 2 to 5 pi over 2, and from 7 pi over 2 to 4 pi. That's where it's positive. And we need it to be greater than 0, not greater than or equal to 0. So that's parentheses. So we'll go ahead and list that out, that it's from, let's practice our interval notation, 0 to pi over 2, union, or 3 pi over 2 to 5 pi over 2, or 7 pi over 2 to 4 pi. Beautiful. That's where it's positive. Where is it negative? everywhere else, but they don't ask about that anyway. All right, next question. I think we got 2 more for this section. Consider the function f of x equals x plus 1 over x plus 2. Find the domain of f. So I do remember we talked about this, that when we have domain, there's 2 rules there's 2 rules currently that we have to think about: fractions and square roots. So here, all that's involved is the fraction. So what's going to make a fraction undefined? What are we going to not be allowed to plug in for x? Well, whatever makes that denominator, whatever makes us divide by 0, because you can't divide by 0. So you solve for x there. You see that happens when x equals -2. So this domain is everything except x equals -2. So we'll say it goes all the way down to -infinity, up to -2, parentheses, because it can't be -2. And then from, what was that? I just got way too many pages advanced. Wait, what? There we are. Here we are. All right, we're back. I thought I was so slick there, moving that to the side, doing that so well. I screwed it up. Oh well, so that's our domain. Anything except -2. All right, B. So then they ask, is the point 1, 1/2 on the graph? It's a good question. What does it mean to be on the graph? That's what we said. It means that when you plug it in, so we can even write, we're doing f of 1. We're plugging in 1 for x. We need to see if that is equal to 1/2, if that actually gets us 1/2 when we input 1 into the function. So we'll just do it. We'll do 1 plus 1 over 1 plus 3. That is 2 over... Hang on. If that's what it was, we might work, but what it actually is 1 plus 1 over 1 plus 2, which gets us 3. So f of 1 is 2, 3. So is the point 1, 1/2 on the graph? Is f of 1 equal to 1/2? No, it's not. The point that's on the graph is 1, 2 over 3. Then I guess if we wanted, we could even say, well, what about when the y value is 1/2? When is the y value 1/2? And that's a bit harder to solve. I'd prefer to just kind of look at this and say, like, oh, it's when x equals 0, isn't it? If you plug in x equals 0, you're just going to get 1/2. So we helped him out a little bit. We said, no, the point that you think is on the graph is not. But these are 2 points that maybe you were thinking of. And then, let's see, they say if x equals 2, what is f of x? What point is on the graph of f? Okay, so now we're doing actually what we just did. So C, they're saying when x equals 2. So they're saying find f of 2. So what is that? 2 plus 1 over 2 plus 2. So that is 3/4. So what point is that on the graph? Well, we plugged in 2, and we got 3/4. So that's x equals 2. Y, or the function itself, is 3/4. D, they say if f of x equals 2, what is x? So here they want the y value to be 2. So we're going to do similar to what we did up there. We might have to do a little more work, though. So we're going to go 2 equals x plus 1 over x plus 2. And then what are we going to do? We shouldn't just think about it. That was just kind of a fluke that worked last time. What I would do is I would multiply both sides by x plus 2. So you've got 2 times x plus 2 equals x plus 1. And then distribute. And then combine like terms. So that over there, you get -3. So when you plug in -3, you should get 2. And if you want, you can quickly confirm that. -3 plus 1 over -3 plus 2 is -2 over -1. Negatives cancel. You do indeed get +2. Okay. E. What are the x-intercepts of the equation, if any? And what points are on the graph? So, like we said last question, how do you always find x-intercepts? You set the y value equal to 0. So, we'll set the entire equation equal to 0. Switch colors. So, we'll go 0 equals x plus 1 over x plus 2. And one cool thing you can always know for when a fraction equals 0 is, well, you can also just think about it, is that if you take a number and you're going to divide it by something and the answer is going to be 0, what does the top of the fraction just have to be? Well, it has to be 0, right? I guess the other alternative is you can multiply both sides by x plus 2 to cancel it out over here. But when you multiply it on this side, x plus 2 times 0, well, anything times 0 is 0. So when you're looking for the x-intercepts of a fraction, it ends up just being the top of the fraction because the bottom of the fraction just cancels out. And so what? You got 0 equals x plus 1, so x equals negative 1. So what is that point? That point is x equals negative 1 and y equals 0. That is our y-intercept, x-intercept, because we plugged in 0 for y and solved for x. All right, so let's go ahead and look at that graph on Desmos. And before we type it in, I think this would be visually nice. Let's plug in everything that we found. Well, we can't plug in the domain, but we can plug in all these points. We could do it in a table. So we found that when x equals 1, y equals 2/3. It's been messing up lately. There we go. We found that when x equals 0, y equals 1/2. We found that we found that when x equals 2, y equals 3/4. And we found that when x equals negative 3, y equals 2. Oh, what was the last thing? We found that when x is negative 1, y is 0. Beautiful. So those are the points that we found. You already see maybe a little curve that's developing there. Let's look at the graph. So parentheses x plus 1 divided by x plus 2. And look at that. Look how all those points we found are indeed on the graph. There's, of course, infinitely more in between, and we can see them here just by hovering over. And when we talk about the domain, if we graph a vertical line and do something like this. Why is that horizontal? What? That should be a vertical line. If you do like x equals 2. Oh, is it because a is just used for something if you do that? So let's do like h. I guess I just need to manually add a slider. That's ridiculous. I've never done that before. So here's our vertical line. And so notice that everywhere we have a vertical line, it crosses somewhere through the graph, except if we put it perfectly right there. So if we put it perfectly right there, now, well, we changed it, so now it crosses through. But if we set it to perfectly right there in the middle, you see, like, no matter how much you zoom, that never touches the graph. And that reflects what we said in our domain, that the domain is everywhere except for negative 2. So yeah, there's a lot to say about graphs, but graphs are just so important. Understanding what a graph is just so important. So here's like a word real situation about it. So the average cost of manufacturing X computers per day is given by the function. Determine the average cost of manufacturing 30 computers, 40 computers, 50 computers. Okay, so they want us to use a calculator here. So we're just going to use a calculator intelligently. And I think I've showed this before, but this is just how the tool we're going to use, is that we're not going to type all these individually. I'm going to actually define the function here. So I'm going to say that c of x, and you can do this in a lot of calculators. Desmos is probably the easiest. It's the easiest to do most things in. But you see I can just directly type the equation in. Plus 1212.57 plus 20,000 divided by x. And then now, what am I trying to find? I'm trying to find 30 computers in one day, and x is the number of computers. So I'm trying to find the C of x, or the C in this case of 30. So now I can just type in Desmos, since I defined what C is. What is C of 30? And it just tells me it's $1,351.54. And then now I just say, what's C of 40? $1,232.97. So what is this? The average cost? This is the cost per computer, not total cost. So that is why you do expect it to go down. This is the more you make, the less it should cost. And then here, oh, did I just eat my words? Did it just go back up? Yeah, it did. And I think that shows that eventually that's like your supply and demand, whatever, kind of meet in the middle type of thing, right? And then we could even look at the graph. So it does say graph the function from 0 to 80. So there's our thing. And then I can show you here that you can do piecewise functions. Like if we wanted to make that graph only from 0 to 80, we can go, let's do C of x. And then this is just like a Desmos thing, really. And then say we only want that when x is between, let's see, it says non-inclusive here. That doesn't really matter. It's 80. And so there, see, it's only the part that we want to graph. So that's what they asked us to do. Now we're only looking at it from 0 to 80. So that's kind of nice because that's where you can see that where your minimum cost per product is. So your minimum, which we saw it closely, was 40. But when we actually look at the graph, it'll show us where the actual minimum cost is. And then what do they just want? They want create a table starting at 1 and doing every 1. Oh, and they just want us to find the minimum with that. Okay, well, so we don't need to do that because we can see the minimum in the graph. But I guess I can show you how to do that. Let's see. Let's say one thing you can do is you can type C of x here. And then, oh, can you not do that? Try defining x. Oh, right, because it's not x exactly. It's x1. It's the numbers that I type in the title in here. So here, I don't know how to just do it automatically. But you see, this is how you can make a table and then type in whatever you want. So it's like if you were trying to do that to find the maximum, you'd be like, or to find the minimum, I guess. You'd say, oh, wow, here we keep going down. The more we make, the more we go down. The more we make, the more we go down. Yep, still going down. And then you'd try 50, and you'd be like, oh, wait, it went back up there. So let's try 45 and say like, oh, wait, that's still higher than 40. And you try 42 maybe. You'd be like, oh, dang, that's still... Oh, no, 42 is lower than 40. Oh, look, it's all showing the points, too. So 42 is lower than 40? But then 41 is also lower? Anyway, yeah. You can just see it on the graph anyway. That's the best way to do it. But yeah, that is 3.2. That is a good introduction to graphs. Next is 3.3, which just talks about different properties of graphs. So that'll be fun. We'll probably get that done tomorrow.